Hi, everyone. Thanks for that awesome introduction, by the way. I'm Anamitra, Datta Majumdar, and I'm a principal engineer at Intuit. My team is responsible for developing security and fraud prevention capabilities. And in my role, actually, I work with all the product development teams, specifically in the small business and enterprise group at Intuit. And some of the flagship products that belong to this group are products like QuickBooks and MailChimp. Now, Intuit is a fintech company that provides payments, money movement, accounting, and tax preparation software for individuals and businesses in the mid-market segment. And some of the other flagship products include TurboTax, Credit Karma, which belong more to the consumer segment. Now, within the small business segment, we have a lot of external APIs that are exposed to third parties. Now, when we look at the statistics, we have around 80 third-party APIs that are being accessed by 17,000 third-party applications that are developed across a community of 50,000 developers, generating almost 250,000 transactions a day. And the APIs are primarily used to share data between QuickBooks customers and the third-party applications, and in the process, enhance the workflows for the customers of QuickBooks. Let's dive into the agenda with that. So we will start by looking at the state of API security and focus on some of the top API security threats out there in the industry. And we will look at some of the complexity hurdles that stand in the way of securing the APIs. Then we will look at some of the security patterns with focus on authentication, authorization, and rate limiting that can be applied in a complex environment. And finally, we'll wrap it around with some of the key takeaways. So companies are rapidly adopting API-first strategy because it allows them to monetize their data, forge profitable partnerships, and open new pathways for innovation and growth. And with this rapid movement, API-first strategy comes its own risks and challenges. Now, this is one of the key statistics around the greatest security risks around API in the industry. We see that the top one is around improper authentication, authorization, and access control, followed closely by sensitive data exposure, and then business logic flaws and insufficient logging and monitoring. And this data was gathered by conducting survey with a diverse range of enterprise organizations that strive to provide a holistic view of their current practices, challenges, and opportunities in API security. And as a part of Intuit trying to secure QuickBooks APIs, we think that this data is applicable to our APIs as well. In other words, these are the top challenges for us too. Okay, from the same report, we see that these are some of the top hurdles that stand in the way of securing the APIs. At Intuit, we have addressed the top two hurdles. However, we are in a journey towards addressing the third and the fourth one by adopting superior prioritization strategies for API controls, and also addressing the lack of a governance process around third-party access to our APIs. Now, what creates all these hurdles that stand in the way of API security? So the coexistence of multiple API types in their environment, like REST, GraphQL, gRPC, the development of APIs by multiple teams across different geographies, coupled with the lack of proper governance across the API development lifecycle stages, and existence of legacy software based on monolithic architectures that needs to be migrated and modernized. So looking at some of the challenges, putting that in the perspective in the realm of the third-party APIs in QuickBooks. So the scale and variety of the API endpoints that serves multiple domains under different bounded contexts creates this challenge and complexity. And added to that, we have 17,000 third-party applications, which kind of makes the complexity exponential. In such environment, we need to make trade-offs between security and usability. Delving into a little bit of details, we need to restrict the access into these APIs by our third-party applications, and by default, the access should be minimized. However, when we are minimizing the access in a complex environment, we see that it impacts some of the usability aspects that our customers encounter. In such cases, we have to make some trade-offs between the security and usability, and that kind of poses a security risk. Now, no matter how complex the environment is, the security controls should be applicable for direct clients, for our third-party clients, for REST APIs, as well as the GraphQL APIs, and must be implemented for multiple levels of trust of our clients, like first-party clients, second-party clients, third-party clients, etc. And the entire data flow should be secure that spans over the clients, the edge of the network, and then back into the domain services. And added to that, when we have legacy services and software in our environment, such architectures are always evolving and getting modernized, and we need to ensure that at each phase of this modernization, we implement these security controls to enforce end-to-end security and defense in depth. With that, let's take a look at some of the secure API design challenges in our environment. So the top challenge is around authentication to the different types of APIs, and then authorizing it to the APIs based on the dimensions of the sensitivity level of the data, a type of operations being performed on the data, or it could be something else that is more relevant to the business context. And also, the other challenge is implementing rate limiting on the access to the data. And this rate limiting can be at multiple levels. There can be baseline rate limiting, as well as very fine-grained business context-specific rate limiting. And these API design challenges are totally correlate with the top security risks that we just saw from the survey. With that, let's look at some of the authentication patterns. So in GraphQL, the authentication can be enabled in the router configuration. So we can enable the JOT authentication, and this can be used to block malicious traffic at the edge of the graph instead of relying on header forwarding to propagate the tokens to the subgraphs. Another directive that is important, and this is more relevant in the realm of access controllers, that ACT authenticated directive, which can be applied to fields and types in the schema. Once it has been applied, what that would mean is those access to those fields or types would require authentication, will require an authenticated session. And the outcome of a successful authentication is usually like we have something called the context, authentication context. When the authentication is successful, the context gets populated and is passed over subsequently to the subgraphs and the other backend services so that it can be used for further access control. Now, taking those controls and applying to a layered, multi-layer architecture is we have an API gateway where we have some logic to kind of discard the unauthenticated traffic at this layer. This is the very first layer. So any traffic that doesn't have any authentication, or in other words, it doesn't have an authorization header, for example, should be discarded in this layer. And then once it gets through, reaches the GraphQL router, then we kind of discard any traffic that has invalid authentication, and then eventually forward it to the subgraph services. And ideally, in the ideal scenario, the subgraph services should validate the identity of the upstream router. And that is usually implemented through mutual TLS or a shared key. These are some of the patterns. And scaling secure API access to third parties, we need to rely on an identity provider that issues access tokens that are restricted by scopes. And these scopes should be taken into account when providing access to the backend services. And the scopes should usually take into account data sensitivity level, the operations being performed on the data, and by default, it should be minimized, and the access to highly sensitive data should really be minimized to the use of the scopes. And also one more thing to mention over here, as I was mentioning, that we have a heterogeneous API environment. So when we have REST-based services as well as GraphQL-based services, there is like a need to introduce some sort of an adapter that converts the REST into GraphQL, and the schema is composed its subgraph schema is composed and put into the supergraph, and it is federated across. Now, taking a little bit of a detailed look, so what truly happens in such a scenario is once the third-party application calls into the router, it passes over the access token, and it in the authorization header, the GraphQL router typically would not understand the access token, so it kind of hands it over to the authorization server, which does the validation, converts it into a JOT token, and sends it back to the GraphQL router, and it is validated and made sure that the session gets authenticated, and the corresponding subject and claims details are extracted and passed over to the backend domain microservices, where further access control can be implemented. By the way, this diagram, this was my first attempt at generating a diagram using generative AI. So some of the key considerations that should be made while implementing authentication in a complex environment is we ideally should have authentication at the router level to reject any invalid traffic at the edge. We should be securing the subgraphs by implementing authentication between the subgraph and the upstream router. And for that matter, like data flow between any components, the downstream recipient of the data should validate the identity of the upstream sender. Authentication should be in place for clients at any trust levels, be it first party, second party, or third party, based on the zero trust principle. And one thing to keep in mind is in certain scenarios, we need to have fields that are public. And we don't really need those fields to be authenticated into. So we can actually, it's okay to not have authenticated such public fields. However, we need to make sure access to those fields are monitored and the traffic patterns to access those fields are closely monitored, and perhaps even have some rate limiting implemented. Now let's look at some of the authorization patterns. So within GraphQL, we have at a high level 2 ways of doing authorization. In the GraphQL layer itself and outside of GraphQL, where we delegate the authorization-related decision-making to an external service. And as I was mentioning, a successful authenticated session has a context value which is passed over to every executing resolver in GraphQL. And this context value object is eventually used to determine what data the user has access to. So now let's take a detailed look at all those 4 patterns. So from left to right, the patterns become increasingly granular and address like greater complexity needs. So in the first pattern, which is a blanket API-wide authorization, we need to have some sort of an authentication across all the APIs. This is usually not suitable in cases where we need to expose public APIs. In the second pattern, where we use the resolvers and the data models, we actually use the context value object that is generated after successful authentication and apply some logic to it so that we can implement access controls to queries, mutations, and fields. And this is, again, like done in the resolvers and data models. In the third variation, we use certain custom directives in the schema, and we can apply it to queries, mutations, and different types of fields and types as well. And once it has been applied to the target, those specific rules for access control gets applied, and within an authenticated session, those rules are enforced. In the fourth pattern, where we implement it outside the GraphQL layer, we make use of coprocessors or plugins or libraries to delegate the authorization decision-making to a service external to GraphQL. And once that service has made a decision around, like, let's say, allow or deny, the decision is enforced for access control. And usually, we would use this pattern for like a more fine-grained access control strategies based on business context domains, implement some custom data governance rules like redaction, tokenization, etc. Now, putting all this into the perspective of our environment at a very high level, what we are doing here at Intuit is we are delegating the decision around authorization to an external service. And how we are doing it is once we have the requests sent from the GraphQL router to the backend graphs, the resolvers take in that information, the authorization header, and uses the authorization library SDK to pass that over to the authorization decision service. The authorization decision service starts consulting the policy. It has some internal mapping of the roles into permissions. Based on that policy, it makes a decision and returns an allow or deny decision. And the resolver starts enforcing the decision and provides subsequent access to the backend service that has the business logic implemented in it. So now some of the key considerations for authorization is we should be adopting a pattern based on the complexity and granularity needs. And specifically for environments that require complex multidimensional policies, we should delegate the decision-making around access control to an external service. And whenever we need to enforce some blanket baseline policies, we should do that at the edge of the GraphQL router. Now, let's take a look at some of the rate limiting patterns. The Apollo router comes with rate limiting constructs. It can be applied to the GraphQL router. It can be applied to the subgraph. And in the case of a router, the rate limiting is applied to the client for traffic coming from the client into the router. And in the case of subgraph rate limiting, the rate limiting rules are applied to the traffic coming from the client to the subgraph. Now, in case of REST APIs, we can implement some coarse-grained rate limiting on the API gateway. However, when there is a need to implement like a business context-specific rate limiting, we need to implement that in the business logic layer. A very good example that we recently did at Intuit is we have an email sending service in our product, and we need to implement rate limiting to prevent that service from sending spam emails to the customers. And such a rate limiting procedure had to be implemented within the business logic layer, together with some coarse-grained rate limiting at the API gateway layer. So with that, let's wrap up. So the GraphQL router comes with multiple authentication, authorization, rate limiting options, as we just saw. So in a complex environment, usually a combination of strategies work the best. For implementing and enforcing complex security policies, usually a proven approach is to have a policy decision service that makes the decision, and then some policy enforcement point that enforces the decision from the policy decision service. And if there is a need to kind of iterate on these policies, we should have a way to iterate independently from the actual subgraph service. We should design the controls based on defense in depth principle and the principles of least privilege with secure defaults, so that no matter how complex the system is, if it fails, it does fail securely. And last but not the least, all parties, be it the first, second, or third parties, they should authenticate to the APIs as a part of the zero trust policy enforcement. So with that, I'm wrapping up, and thanks everyone for attending my session. And please use this link to submit the feedback. And you can catch me at the topic table 1:15 p.m. onwards. Thank you.